There is a dam in the Nevada desert hiding a secret most engineers never told you. It stands 726 feet tall and weighs over 7 million tons. And hidden inside it runs nearly 600 miles of steel pipe. Had engineers used the conventional methods of the time, Hoover Dam would still be cooling down today. The concrete would have cracked. The dam would have failed. And the American Southwest would be a desert without water or power. 40 million people depend on this wall today. The question nobody asks is, how did they beat the physics? This is epic engineering. And if you haven't subscribed yet, this is the video that will change that. Hit like, subscribe, and ring the bell. Every notification helps us keep bringing engineering at this level straight to you. Now travel back with us to 1931. To understand what was built here, you first need to understand what had to be tamed. The Colorado River was not a river. It was an annual death sentence. Every spring, snowmelt from the Rockies turned this calm river into a wall of water and mud. Entire towns across Arizona and California lived under the constant threat of being wiped out. Farmers who had spent years building a life lost everything in a matter of days. In summer, that same river ran dry. The region that drowned in spring would die of thirst by August. When the federal government decided to tame the Colorado, the country was deep in the worst economic crisis in its history. 16,000 men came from every corner of the United States looking for work. Many brought their families. What they found was a canyon with vertical walls rising nearly 1,000 feet and heat reaching 130 degrees Fahrenheit inside the tunnels. Before a single bucket of concrete could be poured, the walls had to be cleaned. Men rappelled down on simple ropes, suspended over the void, blasting and hammering loose rock by hand. They were called the High Scalers. They became local legends. They earned production bonuses and risked their lives on every descent. Before a single foot of dam could rise, the entire river had to be diverted. 4 tunnels, each 56 feet in diameter, were carved through the canyon walls to drain the riverbed. For the first time in history, the Colorado River stopped. The riverbed lay bare under the open sky. There, on a floor that had never seen sunlight, the work began. The first concrete was poured in June 1933, and that was the precise moment the real problem revealed itself. It wasn't the river. It wasn't the desert. It was the concrete itself that threatened to bring everything down. Because concrete, when it cures, doesn't simply harden. It burns. When Portland cement meets water, a chemical reaction begins that cannot be paused, sped up, or reversed. It releases heat. A lot of heat. In a small block, that's harmless enough. The heat escapes through the surface. But Hoover Dam is nowhere near a small block. It's a 726-foot wall containing 2.6 million cubic yards of concrete. At that scale, the heat has nowhere to go. It stays locked inside the mass. The calculations showed that internal temperatures would climb 40 degrees Fahrenheit above ambient during the curing process. The danger wasn't just the heat itself. It was the temperature gap between the hot core and the cool surface. That gap creates stress, and stress creates cracks. Poured as a single mass, Hoover Dam would have taken 125 years to cool down naturally. Inauguration was in 1936. Natural cooling would have finished around 2061. The engineers at 6 companies knew this before the first truck of concrete ever rolled in. The solution they came up with is what makes this structure unlike anything else ever built. Instead of one solid mass, the dam was built as a series of interlocking trapezoidal columns, each column a separate block, each block an individually controlled unit. Inside each column, engineers installed a network of 1-inch steel pipes, thin-walled and precisely laid. In total, 582 miles of pipe. That's the distance from Las Vegas to San Francisco. Phase 1 was straightforward. Natural river water circulated through the pipes, pulling the initial heat out and dropping temperatures from 115 down to 70 degrees Fahrenheit. Then came the refrigeration plant, a machine capable of producing 1,000 tons of ice every single day. Water chilled to 40 degrees. Fahrenheit was pumped section by section through the pipes until each block reached its precise target temperature. There was no rushing it. Every section was monitored individually. Cooling a single column could take weeks. Once the temperature hit its mark, the pipes were filled with cement grout under 300 pounds per square inch of pressure. The veins became bone. What had started as hundreds of separate blocks became, piece by piece, a single concrete monolith. Among the engineers on the project, this system became known as the concrete refrigerator. In the description below, you'll find links to great material on Hoover Dam to learn more and have a great time doing it. There's one more detail most people never hear. This concrete never stopped growing. Core samples taken decades after the inauguration show that Hoover Dam is significantly stronger today than it was when construction finished. The concrete keeps curing, keeps gaining strength. The dam engineers handed over in 1936 is not the same structure that stands today. Taming the heat was only half the challenge. The dam still had to do something with all that stored water. Water from Lake Mead descends through steel pipes 30 feet across. At the bottom, it arrives under 300 pounds per square inch of pressure, the equivalent of a 650-foot column of water pressing down on your head. Down there, it meets the Francis turbines. Unlike a standard water wheel, water enters from the sides and exits through the bottom in a spiral flow that converts up to 90% of kinetic energy into electricity. There are 17 turbines. Each one turns a solid steel shaft nearly 3 feet across. Each rotating assembly weighs 700 tons and spins at 180 revolutions per minute around the clock. The greatest enemy of these machines is not wear and tear. It's cavitation. When pressure drops below a critical threshold, water boils cold, forming bubbles that implode against the steel with destructive force. Those implosions eat through steel like it's paper. Engineers continuously monitor the blades to catch the problem before it becomes irreversible. Now, look at Lake Mead differently. This reservoir holds 78 trillion pounds of water. That load is so immense that the Earth's crust beneath the lake sank 7 inches. Solid rock behaved like a mattress. The filling of the reservoir in the 1930s triggered hundreds of micro-earthquakes. It was one of the first documented cases of man-made seismic activity in history. To understand what happened to the Earth itself, think of a figure skater. Arms out, she spins slowly. Arms in, she spins fast. By moving billions of tons of water from the ocean to a mountain reservoir, we changed the distribution of mass across the entire planet. Hoover Dam, along with other large reservoirs, measurably altered the speed of Earth's rotation. The shift is billionths of a second per day. Real, measurable, and documented by NASA. 5 years. Delivered 2 years ahead of schedule. 16,000 men who arrived with nothing and left behind one of the greatest structures in human history. 96 deaths were officially recorded during construction, each one with a name, a date, and a cause. There's a myth that says bodies are buried inside the concrete. There aren't. Concrete was poured in layers just 6 to 12 inches thick. A body would have been spotted immediately. The myth is false, but the 96 deaths are real, and they deserve to be remembered by name, not by legend. Today, Hoover Dam supplies water and power to 40 million people across 3 states: Nevada, Arizona, and California. And inside that wall, all 582 miles of steel pipe are still there, filled with cement, part of the structure, invisible. The concrete keeps curing, growing stronger than it was on the day it opened. This project didn't just beat the desert or the river. It was a victory over physics itself, fought with steel pipes, chilled water, and a precision the era could barely imagine. If this video changed the way you see engineering, the next one will do the same. Subscribe, hit the bell, and we'll see you at the next great build.